Welcome to the second meeting of UBC-Tongji CSI Symposium. It's very good that all of you are here this morning to support our program. And give me a great pleasure to quickly introduce our session chair for this morning. That will be Professor Frank Lane from UBC and Professor He from Tongji University. I'm sure you're here to listen to a very exciting series about wood structure research. Frank, I'll quickly give it to you so you can start it, whatever you need. Thank you.
Thank you, Tony, for the kind introduction. And this session this morning is the Team 4 on timber structure. My name is Frank Lam. I reside in this building. And my area of interest is, of course, in timber structures. We have 4 talks this morning. The first talk is is a keynote speech from Tongji, from Professor He. Professor He, we know of her for many years. She's a good friend. I visit her probably once a year at least, and she does likewise. She started on the timber research area probably more than 10 years ago, and with collaboration with Canada, and she's one of the top experts in China on timber engineering. So she's going to tell us a bit about the recent research on timber structures in China. Okay, without further ado, Professor He.
Really? Oh, I think I can speak not enough. Yeah. Forward, backward. Yeah. Good morning, ladies and gentlemen. I'm pleased here to introduce some recent research on timber engineering at Tongji University. I will introduce 4 parts. First, as you know, in China, there are very long history on timber engineering. About 3,500 years ago, we started to build post and beam timber constructions connected by mortars and tenons. And there are some old buildings exist now. Ancient pagoda. You are familiar with the Gugong. From 50s to 70s last century, brick and concrete timber hybrid structures were built in a lot of areas in China. Second part, issues on the development of timber structure in China. In the 1980s, concerning the large population and the shortage of wood resources, our government restricted people to use timber as construction material. But recent 10 years, with the increase of imported wood resources and local fast-planted forests, our government encouraged to use timber as a kind of building material because of the green and sustainable buildings. We have a lot of application of timber structures, such as the wood frame construction in residence houses. These are residence houses in Beijing and Shanghai. And we also use wood frame construction in public buildings, such as some school buildings and some tourism buildings and conference center. And other public buildings, such as a toll gate in Yunnan province, entrance of Chengdu Happy Valley, and this is the roller coaster in Shanghai. I think a lot of you familiar with it. And the bridge, club. Also, there are some new buildings. This is the building cellar sector in Jilin, and this one is the toilet sector in Qingdao. In the 2010 Expo in Shanghai, there are a lot of timber structures. This is the Norway pavilion, and this is Sweden pavilion. And we also use glulam structures in rebuilding of temples, the old buildings. This is the Xiangji Temple in Hangzhou. And this one is the Lao Junge in Sichuan. And we also built some hybrid structures. This is the 2000 Shanghai Expo building, Vancouver Pavilion. In the construction of the timber structure, we also faced some problems. First one is, how about wood frame residence house? About 10 years ago, built a lot of residence houses with wood frame. But some people say, how to solve the problem of limited land resource? Because in China, there are very big population, and everyone have we have a limited land resource. But for the wood frame, we only can build low-rise building. So the ratio of the land utilization is very low. So how to solve this problem? And on the other hand, our Chinese people like some timber structures. We can touch it, we can saw. This is wood. So more people like glulam structures. But in the glulam structures, wood frame also can work as the wall panel. The other problem glulam construction faced, how to increase lateral resistance, stress, and rigidity for post-beam construction. As you know, in the post and beam constructions, the structure made of posts and beams. How to increase the lateral resistance capacity? The connection between column and the beams can be look like joint. So we need to increase the rigidity of this kind of connection. How? The other question is about timber construction. What kind of timber structures, wood frame or glulam structures? How to increase the ratio of land utilization? How to prove the fire resistance or the durability? These people take care of. Regarding these problems, we do some research in our university. At first, in the beginning of the 2000s, let people understand this kind of structures, wood frame construction. So we do some tests to recognize this kind of structures. This is the load-bearing capacity of the truss, wood truss. From tests, we can know some failure mode of this kind of structures. And this is the connection test about the wood frame constructions. And this is the shear wall test. From the shear wall test, we recognize the different wood-based panels shear walls. And the load-bearing capacity with these different kind of wood panels. And from the test, we also recognize the gypsum resistability. And from the tests, we got some model and do some numerical modeling. We also did the seismic performance shaking table tests. From the tests, we know the lateral resistance of this kind of constructions. And we also do some 3D numeric modeling of this kind of structures. And based on a lot of real projects, we do some field measurement. And based on this field measurement, we also do some numerical modeling. The second part about research is glue-line connections. I mentioned that we would like to know how to improve the joint rigidity of this kind of structures. So we do some performance of post and beam joints tests. And we also do some tests about the combining the lateral performance, combining of wood frame and post and beam. From the tests, we can know the property of their work and do some numerical model. We also do some full-size connection tests of real projects. This kind of connection will be used a real project we call Nuohua projects, and the beam is big and the connection also is big. So we would like to know the load-bearing capacity from the tests. We also are interested in the hybrid structures because we know in China there are very big population, and for the pure timber structures only can build low-rise buildings. So we would like to increase the application of timber and to build multi-story buildings or high-rise timber buildings. So at the beginning we do some comparison between timber structures and other kind of structures. As you know, this is the building of our college. It is steel constructions. We do some analyze. If we use wood floor, replace instead of the channel steel and concrete composite floor. How about that? From the comparison calculation, we can get to the conclusion that if we use the timber floor, we can decrease total structure weight about 23%, and we can decrease the seismic action about 32%, and decrease vertical loads on foundation about 48%. So I think it can be a choice if we use the wood floor. And we also do some tests about timber and concrete structure tests. This is a one-story building. It's a concrete frame, and we also use timber diaphragm. From the tests, we can get some results about the action of the diaphragm, timber wood frame diaphragm. We also do some timber and concrete structure modeling, 3D numerical modeling. And we also do some shake table tests of timber concrete hybrid structures. From the shaking table test, we can get to know the property of this kind of structures, and design how to set up the design methods. And as a concept about steel timber hybrid structures, we model this kind of structures. We use timber diaphragm and light wood frame shear wall and steel frame. From the timber diaphragm and the steel frame, we form the horizontal systems to resist horizontal force in the horizontal level, and we use the steel frame and the wood frame shear wall. We form the vertical system to resist horizontal loads. This is the steel hybrid from wood frame. In this wood frame, it is made up of the steel channel steel and the wood panel. And this is the shear wall, vertical system to resistant horizontal load. This is the steel column and beam, and this is the wood frame shear wall. And this is the tests of these hybrid structures. From these tests, we can recognize the failure mode and lateral resistance capacity. And we also do some connections in this kind of hybrid structures. This is the tests for timber steel hybrid diaphragm structures. This is the numerical modeling of this kind of structures. So I introduced some application of timber structures in China and also introduced some research in our universities. From the research and from the application, we get to some conclusion that because of the big population in China, we think, first we think timber structure is a kind of natural resource-saving energy facility technique and low carbon emission. So we like to use timber as a building material. And for the big population, we try to use timber in multi-story buildings, and so we set up some model of timber hybrid structures. Thanks.
Are there any questions for Professor He?
I just have a question. For the show one illustration of steel channels and top panels, but do you basically copy?
Yeah. 30-meter topping of concrete.
Are there any shear connection between the concrete and the wood?
Yeah. Some kind of particular nail. Yeah.
Any other questions? Maybe one more question? Well, if not, please join me to thank Professor He for very I'm actually the next speaker, so I've already introduced both. Dr. Yang has already introduced myself, so I don't have to introduce myself again, so I can go directly to my talk. Thank you. Yeah. So I don't have access to the red and yellow card, so hopefully I won't go over time. Okay, good morning. I'm going to just talk a little bit about recent research activities on cross-laminated timber as well as glulam material at UBC. I'm just going to go very quickly and briefly over some of the projects because there's not enough opportunity to go into details. First of all, just introduces cross-laminated timber. It consists of layers of wood that are laminated on the face of the material. The glue is applied on the face of the material, and the cross layers are usually orientated at 90 degrees to each other. In this way, you can form very thick panels. Up to 9 layers are made in Europe, and about 0.3 meters deep, and in some cases almost half a meter deep, and the length can be around 16 meters long. It can be longer, but because of transportation, the limit is 16 meters. Width usually around 3 meters. So you can think of these as thick plates, very stiff, very in this plane is very stiff and strong. So this is a picture I took in Austria in the manufacturing facilities. There's a foam panel that came out of the press. So with this type of material, there's new opportunities to use thick plate rather than the usual post and beam or 2x4 type construction techniques. So it's generated a lot of interest in Europe, first of all, and now more recently in North America for application of these type of panels. Of course, with the new material, we need to do research to understand how they would perform. And in particular, one of the issues for British Columbia is that our forest has been attacked by this little insect. The beetle is a mountain pine beetle. The size of the insect is so very tiny. It's smaller than your pinky, okay? But it has decimated our forest. It killed approximately 18 million hectares of forest land in British Columbia. So how big is that? That's combined forest land in Austria, in Germany, and in Switzerland together. How much wood is there? Enough wood to supply the glulam industry in Europe for over between 50 to 100 years. So the wood that is being destroyed, the volume is tremendous. Now, two things can happen to the wood. Well, three things. You can either use it. If you leave it in the forest, it can go decay, it can rot, or you can have forest fire, it can burn. Okay? So the last two, of course, we don't want, and we need to find usage of this wood as soon as possible before it goes become rotten or burnt. Where can you use this wood? Normally, this wood is used to supply the U.S. market for building these small homes, our homes. But our population is not increasing to demand additional use of the wood in a very short time. So we need to think of alternative. One of the alternative, of course, in my view, is to apply this in these thick and heavy timber construction for buildings, for example, like ours, mid-rise, medium-rise buildings. And our government British Columbia government has also taken very aggressive actions. They have allowed about 4 years ago up to 6 stories wood frame construction to be built for residential building. And also they have a rule that says that if you want to build public buildings, if you want buildings that requires money from the government, you must consider, but you don't have to use it, you have to consider the use of wood. Now they generated some interest from architects and engineers and developers to start to think more about using wood. And now in Europe, these CLT buildings have been used for small buildings, for some 3-4 story buildings. This is one of the first ones in Austria being built. And maybe 5 years ago, they built this 8-story building. It's actually 9-story with 1-story reinforced concrete in the bottom of CLT building in London. So now people can begin to see that you can build tall buildings too with wood. More recently in Australia, in Melbourne, this is a 10-story CLT building. Again, 9-story of wood and 1-story of reinforced concrete. So it offers some excitement. People beginning to want to see tall buildings being built. And in UBC, if you walk around campus, you will see some buildings built with CLT. This is a industry bioenergy plant that generate electricity as well as heat for the university. You can see CLT being used at the first picture is the wall system, and then this is the roof system. But when you see this heavy timber construction, you know always glulam is
usually involved to help span the longer distances. Another very beautiful building is the Earth Sciences building on campus. Again, you can see CLT being used as the canopy, and also the roof is a CLT structure. Now, so I mentioned that research needed to be done. There's lots of work being done by the industry already on this area, FP innovation in particular. But we, at the universities, we have also initiated research work in this area. One of the key programs that's been funded by our national government, the NSERC, is a strategic network that involves many universities in Canada. And there are 4 themes. I lead the theme on CLT, under which there are a series of projects that are being conducted on CLT. And I'm just going to briefly talk about some of the projects that UBC is involved in. So one of the key things that we wanted to do is that we say that, hey, our resource, our wood, is different from European wood. So if you want to make CLT using our wood, we better understand how to make it using our wood, what type of manufacturing parameters are needed that is best suited for using our wood. So there's a project that involves a big project, 5-year project, involves PhD students as well as postdoc fellows on this topic. And I'll talk a little bit more about this. There's a project that is starting actually this year in reinforcing CLT systems for this rolling shear failure. And I'll talk about rolling shear, but I won't go into detail about this topic. So how to make CLT? Well, what type of glue you use will be important, right? If you think about gluing these panels together. In Europe, in Canada, the type of glue that we use to make these heavy timber usually is PRF. It is a very, if you go outside, you see the parallelogram beams and the columns. The dark glue is the PRF glue. It's either requires heat or require longer pressing time. In Europe, they use this PU glue, which is a polyurethane glue. It is faster to glue up, but it has some properties that are not the same as PRF. So we want to understand what's the difference between these two when we apply to our species of wood. The beetle kill material belongs to this species group, SPF, so we want to study that. But there's another important species on the coast dealing with the bigger trees that we want to study to make sure that if we want to use CLT, whether we can also include this as a species group. Different grade of wood, whether you use very high quality materials such as the European ones, or you can allow a bit less quality, but yet achieve certain level of performance that you want to target. How you press these panels? Do you need to have the big press to apply high pressure, or can you get away with lower pressure to make these panels? So these are some of the manufacturing parameters that we studied. And one of the PhD students has finished her work, developed computer models as well as experimental database that deals with this aspect of the work. Ongoing study is with a postdoc fellow, Dr. Lee, and as well as a student actually from Tongji University. Both of them are from Tongji. Alex Li Yuan, they're studying the performance of CLT under short and long-term loading. So in order to do this, you need to make the panels. At the time, no industry was making these panels. People were actually shipping panels from Europe to do the study at Canada. In Canada, we didn't want to do that. We actually make our own panels and study the performance. This is our plain loading. The shear stiffness and strength of the connection, of the glue connection, is important. So we derive a fairly innovative way to study the bond strength and the stiffness as a function of the different species, different types of glue, and different pressing pressure on the material. You can see we have a ring of adhesive, and then we almost like a torque tube type exercise that we establish the the shear strength as a function of different parameters. And you can see that it does depend on how you make the panel, that you can have different performance in terms of the shear bond. With this information, we can put it in FEM models. We also need the elastic properties of the wood, and then we can predict the stresses in the material. One of the failure mode that we observe is so-called rolling shear failure mode, where the material actually fail in the middle layers in shear, first in rolling shear and then in longitudinal shear. This is more of a governing situation when you have short span to depth ratio, and longer span usually is deflection governed. And we went beyond that. We say, what's the next generation of CLT? Perhaps we can have box structure. So in here we have CLT panels on top and bottom, and then ribs going across. So we have a form of box structure that's stiffer and probably more better suited for long span applications. For the rolling shear, if you can imagine, if you have a concentrated load through point support, it becomes important. Now, if you look at our code, there's very little information on rolling shear behavior of wood, solid wood. So we were doing, rather than looking at big panels, we then cut little strips of the panels to look at this in more detail in small specimen studies. And we can then also predict the performance using models, calibrated models. But more importantly, in our code, we know that wood may be able to sustain a load in short term, but the same load applied in the long term may fail eventually. So this durational load behavior is not well understood for rolling shear material. So there's a void of information in here, and we are doing study at this moment. So, but rather than applying a sustained load, what we do is that we want to apply a repeated load, kind of creating a damage accumulation situation for the wood, and try to predict this performance using models, either stress wave model as developed by Professor Foskey and Mr. Yao in the back, or other models that we worked on that is based on displacement or strain base. So that's on the material behavior. But on the system behavior, there's much more that also needed to be done, and there are a series of topics that is currently underway. We finished one of these that is jointly supervised by myself and Terry Huckers at UBC. We have other projects that's ongoing. Dr. Yang and Terry is also involved in some of these, in particular dealing with the seismic response of these CLT buildings. But in all these work, you can think of the CLT panel as a very stiff and rigid material in plane. So what is key to this is the connectivity between the panels, how you connect them. And people have done a lot of research on big system, driving screws in it. And I think it's more important to look at the small system to understand what's going on. In this particular case, we apply the screws at an angle, first this direction, and so it's a double angle. So 45 degrees in this direction, and then 45 degrees in this direction. So the screw is going in an angle this way, at a double angle. Why is that? Well, these type of screws are most effective along this axial direction in tension. So under this way, when we apply a lateral load, the tensile action of the screws are activated, and it's much more effective as you just put the screw at an angle, at one angle through the panel. And using these techniques, we actually helped the designer to build the bioenergy building, the Nextera building on campus. And this is an innovative part of some of the work that we have done. With this information, the student can again model the system. Again, the plate can be considered as a fairly rigid material, and all this action comes from the connector. So with this we can also look into taller systems as a wall system. That was what for a diaphragm system that we looked at. Okay, when we have taller walls, some of the issues of the stability of the walls may become of importance. And in this case, rather than putting a heavy load on the wall unit, we cut strips and look at the CLT as a column subjected to axial load with a small small load, lateral load applied just to kickstart the motions. So we can have see some of the details. The end supports are we try to get a fixed support, because if you have a pin support, sometimes the friction is very difficult to quantify under rotation, and it can interfere with the results. You can see the failure mode eventually usually is a compression failure, and eventually is a tension failure at the other side. But what we find is that if we use the current recommended procedures to design such system, it is way too conservative, because they ignore the contribution of the cross layers, and that can be a significant difference between what the material actually can behave and what you think it behaves. When we talk about big buildings, large important question is fire response. So I was lucky enough to collaborate with colleagues in Europe, where they would do these tests for me for free. So we were able to conduct a series of fire tests. This is a floor system under unfactored design live load, and then in the chamber is a standard fire being burned. You can see the clock, they monitor the movement and the time, as well as whether the system has failed or not, right? So this way is one way of quantifying the behavior of wood system under fire. This is a test for a wall system. The fire is set in the chamber behind it, and this section is under vertical load. Okay, so you can see when you take out the specimen, it is fairly hot. Structurally, this is very interesting, because it is a extremely nonlinear system with a vertical load and a degrading surface on the inside. So the failure mode, actually, you can see buckling of the panel as the experiment progresses. But at the moment, what the code people are interested in is the charring rate. They see how much wood char under the standard fire, and then establish a rate of char for the wood type of material, and apply this for design. Okay. What we find is that the charring rate is, at least from this experiment, is slightly higher than what they were hoping the material to behave. It's around 0.72 rather than 0.65 or so. But I think it's within the ballpark that we talk about. So one of the reasons why it's different is because of the glue. The glue under heat can soften and can detach it from the specimen. So once the char layer detaches, then the additional material starts to burn and char. So hence there's an increase of rate of charring in the material. We have this information for both vertical wall application as well as for floors. And I think the next step we want to do is to model this in structure analysis. Yellow card now. Okay, so only if I'm ready. Yes, in Gulam, this heavy timber construction, one of the issues is that the bigger the member it is, the strength, that's the load per unit volume, is actually decreases. So this is one characteristic of wood. So we are involved in testing of some big members. The biggest members we tested were actually done in the US because we don't have enough facilities. They were almost 22 meter deep beams, 1.2 meter tall. What we have combined this with computer prediction approaches using computer program that Professor Foskey developed with his student Brian Foltz. And the predictions are very good compared to different sizes of material that we tested. So this is the current Canadian code. So it says that if you have a string volume or size more than a certain amount, you take a constant strength. Bigger, you have a decrease in strength. The red dots are experimental results, and the blue dots are predicted by a computer program. And this slotted line is a approach that we are recommending to the core committee based on a volume-based adjustment factor. So we would allow smaller beams to take on bigger load, and bigger beams to take similar decrease in load. The biggest beam we tested have a strength lower than what we were expecting, but in this case, there's some issues with regard to the beam that was actually tested, as well as in these big beams usually it's governed by deflection. So I think we will still be safe in here. We can compare this, fitted the results to the log of the volume, and and we can see that the linearity is quite good. We also dig back into the old database. US has some big beams also tested in the past, and they are pretty well in agreement with what we have observed. So I'm going to close with this slide. I think we need to continue forward, and really the key, if we want to build safer, more economical, and bigger buildings, we need to look into connection behavior. We have to look at it from the repeated loading to seismic action, and also the behavior of these connections under fire is really not well understood. In the system response, if you look at the entire structures, of course you need information from before. Again, fire and seismic issues are important. Now, perhaps you want to think ahead. When you have an earthquake, maybe fire can also start. So what is the combined risk when you have an earthquake and a fire, and how do you protect buildings in this situation? We usually think the sprinkler will offer some sort of safety, but what if the earthquake knock out the water supply? So maybe these heavy timber systems, you may have to think carefully how to address them. Maybe you need to have these systems that can self-extinguish during fire attacks. Just a couple of thoughts. This building is in Vancouver. If you go down to the gas town, it's still here. It was built in 1905. It's a heavy timber construction, 7-story building. So we knew how to build this tall building in the past. Going back a bit more in history, go back to China. This is the building in Shanxi, Yinshan wooden pagoda, built almost 1,000 years ago. It's still here, 66 meter tall, still the tallest wood building in the world. Okay, it used to be taller. It used to be 67.5, but there was some problem with compression perp. Okay, so there's serviceability issues that need to be considered when you deal with tall buildings. Make sure that you not only seismic and so on, you need to have other issues to thought about carefully. That's it. Thank you very much. Any questions?
Do you know how many cubic of the COT windows should be transmitted?
How many cubic meters COT is used to build 1 square meter buildings? I don't have the information. Yeah. No, that was done in Italy. these fire resistance tests are very expensive. Each test will cost, typically cost 50,000 Canadian dollars. Okay, so that's 300,000 31 renminbi. So very expensive. So my friend in Italy is very kind. He says that you can do it for free. So immediately I ran over and did the test over there. Because of the smoke, yeah. In here, the smoke was just ventilated out into the atmosphere because that lab is far away from the city. Okay, so but I would be very careful about the smoke because the glue could be, if you burn the glue, it could be very harmful, especially PU glue, very harmful. Yeah, so yeah.
And I have one question. And when you talk about the rolling shear in the VLT wall, I just wondering, is that possible to use self-tapping screws or the glued-in roll as a replacement to replace?
So that is one of the. So the question is, when you have rolling shear failure, can you use screws to reinforce it? Yes, this is one of the ideas and one of the topics that we were going to study. With a student that's supposed to be here from Tongji University. But yes, there's already a thesis done in Europe using rolling screws to reinforce it. But I think it's a bit expensive to do so because the screws are not cheap, right? Maybe $4 each. So I'm looking at perhaps to get the student look at alternative ways to do the reinforcement. Yes, particularly for point support situation. Yeah.
Frank, as I'm sure you know, there's some people in the industry who are hoping to codify CLT as a seismic force-resistant system in the Canadian Code for relatively tall buildings.
Yeah.
It's not happening, I guess. But I just wondered if you can comment about the research you're doing in that area.
Yeah. Yeah.
CLT is a seismic force-resistant system.
Yeah. So people want to, the industry want to push this to tall buildings. They want to look at 15, 20-story buildings using CLT system. The key issue is the ductility factor. One of the key issues is ductility factors. What ductility factors and what overstrength factor do you assign to this? That's fine. But I think fundamentally, one needs to look at the connective system. Really, right now they've done tests using screws. They take big panels, cut it into small panels, and then put in screws, and use the screws as a way, these connections as a way to dissipate energy, which is one concept. But there are so many other possibilities. You can take a big panel, tilt it up, and use it as a panel by itself, and look for other ways of taking out the energy from the earthquake, right? So I think there's still a long road that one need to go. There may be one particular system that could work under the recommendation and could work rather, let's say, erring on the safe side, but that may not be the most economical solution. And in that sense, I think more research really is needed. Of course, we want to compete with the reinforced concrete guys, and we need to have a very good answer at the end. Yeah.
You guys are doing work in that area?
We are doing work in that area. We're working with Tony and Terry on this area. Some of the students are here already, and some of them are still on the way to come. So we want to really focus our attention on this area. But from the basics, from the connectivity point of view first, really understand what are the options so that we can go at that. Yeah. Oh, I got my red card now. Thank you very much. Okay, so we have to go on to the next presentation. We're a bit behind in time, but we're okay. Yeah. So our next presentation is from Mr. Liu Yingyang from Tongji University. He's going to give a presentation on experimental study on lateral resistance of timber post and beam structures. Right? Thank you. Oh.
Supervisor at Symposium, and the topic today is the experimental study on lateral resistance of post and beam structures. And here's the content of the report. And usually there are two kinds of timber structure system. One is a large frame wood constructions. It is common in Vancouver, and this kind of building composed of wood frame shear walls and timber floors and timber roofs. The other is the post and beam structures. Sometimes we call it heavy timber structure compared to the light frame wood constructions. And this kind of building have two types of members, the column and the beams. In our test, we have 10 specimens, and three are pure post and beam structures. That is to say, the embrace structures, and 3 X-brace structure, and 2 K-brace structure, and 1 knee brace structure, and 1 filling lat wood shear wall structures. And for the spec numbers, the F stands for post and beam structure, and the SP, KB, HP stand for X-brace, K-brace, and knee brace, and the W stand for lat frame wood shear walls, and M stand for monotonic test, and C stand for cyclic test. Here's a picture of our test. The test was carried out by the state test system of CTK laboratory of Tongji University, and our experimental study mainly focused on the in-plane lateral resistance without considering the lateral load, vertical load, and the out-of-plane stability are ensured by steel rollers on the gantries, and the test instrumentation are as follows. First, the loading force exported directly by the shrink machines, and the horizontal displacement of the top of the column, and the rotation of the joint, and the horizontal slip and pulling up of the bottom column. And here's the test procedure. We referred to the standard of American society testing material. And here's the monotonic test. And for the cyclic test, there are two displacement patterns. The first displacement patterns have 5-4 single fully reversed circle at displacements of 1.25%, 2.5%, 5%, 7.5%, and 10% of the ultimate displacement. And the second displacement pattern consists of phrases, each containing 3 fully reversed circle of equal amplitude at displacements of 20%, 40%, 60%, 80%, and so on until the ultimate load is reached. Our test failure criteria is there are two. One is the load decrease to 80% of the ultimate load, and the other is the lateral displacement turned to 250 millimeters. That is to say, the in-stroke drift angle turned to 1/10, and we consider it the structure cannot bear the load anymore. And here's the experimental phenomenon and failure model. For embrace structures, when the lateral displacement turned to 10% of the ultimate displacement, the joint showing up local pricing close. Here's a picture of local pricing close. Take the post and beam joint. For example, the local pricing close change the way of the force transmitting. For the indirectly load transmit, first the load to the column, and then to the bolts on the column, and then to the steel plate, and then to the bolts on the beam, and then to the beam. The other way is the direct load transmitting through the local pricing close, and the column bottom joint is similar to it. And as the lateral displacement increased, the cleavage character, that is to say the wood splitting, first appeared on the bottom column joint and then appeared on the ends of the beam. And in the subsequent loading process, the cleavage character developed. This is the final failure model of the embrace structures. The destruction only found in the joint, and the middle spine of the beam and column was intact, showing up the weak joint and the strong members. This is different from the structures made by steel and concrete. And this is the express structures. And when the lateral displacements were small, there are no significant destruction phenomena, only some sound made by the connection of the wood and the bolts. And when the lateral displacement turned to 60 millimeters and to 24 millimeters, there are outer plane deformation appeared on the brace. This is applying thrust load, and this is applying pulling load. And when the lateral displacement turned to 32 millimeters, when applying thrust load, and in this time, the tension element of the brace split, but the compressive one was intact. And when pulled the structure back, the previous compressive one turned to a tension one, and at this time it split. And in the third circle, the significant load drop showing up the destruction of the structure. And this is the final failure model of CSB1. And CSB2 is similar to CSB1. Here is a video of the whole load processing of CSB1. When the lateral displacements were small, there are no significant phenomena. And as the lateral displacement increase, there are slightly rotation at the brace joint. We can see from it. When the lateral displacement turned to 80% of the ultimate displacement, the tension element of the brace split firstly. In the second circle, you can see the splitting. Oh, here's it. This is the final failure model of CSB1. And for the K-brace structures, at the earlier load processing, there are slightly rotation at the brace joint, and the cleavage characters appeared on the beam on the bottom column joint. And as the lateral displacement turned large, the bolts of the brace joint were cut. When the bolts are cut, gradually the brace loses connection with the structures, and this is the failure model of the K-brace structures. For knee brace structures, it is similar to the K-brace structures. There are also the bolts cut at the brace joint, but a different thing is that the knee brace structures, when the bolts were cut, the wooden brace was stuck in the wooden frame, still transferring the compressive load. This is the whole view of the knee brace structure. From this picture, we can see clearly when applying thrust load, the left brace is out of work. It does lose a connection with the structure, but the but the right brace can still transfer the compressive load, and when pulling back, the situation is similar. And because of this, it maintains the load-bearing capacity and showing up a good ductility. About the fitting lateral shear wall structures, as the lateral displacement increased, the new joint generally filled. This is the failure model of the new joint. This is stuck in the panels, and this is the bending, and this is the pulling out from the panels. As the new joint become invalid gradually, the panels extract from the studs and leading to a staggered displacement between the panels. This is the staggered displacement between the panels, but it is because the wooden frame, the hooping effort makes all the components working together, showing up a good ductility. And this is the final fitting model of the fitting in lateral shear wall structure. After the experiment, we deal with the result, and this is the hysteresis curve of the specimens. And the first two are unbraced structures, showing a low lateral stiffness, while the X-braced structures, K-braced structures show a high lateral stiffness. But the failure mode of these two kind of structure systems belong to brittle failure. And for the knee-braced structures and fitting lateral shear wall structures, it has a good ductility and energy consumption. And for the ductility, I think is the hooping effort of the wooden frame that provides it. And the energy dissipation, I think, is the friction between components and the wood splitting that provides the energy consumption. We took the envelope curve from the hysteresis curve, and from the envelope curve we can find the peak load and the failure load and the alternate lateral displacement. And we use EEP method, that is to say the equipment, energy, electric, and plastic curves. We found the yield point, and this is the main mechanical performance parameters. Oh yeah. And the last column is the installed drift angles of all the specimens. And according to North American standard tolerance of the installed drift angles, in the mineral earthquake is 1%, and in the moderate earthquake is 2%, and in the major earthquake is 3%. And from this, we consider the X-brace and the K-brace and the fitting lateral wood structures can meet the normal requirement of the normal use of the buildings. And for the knee brace structures, it improved compared with the hand-brace structure. But I think the installed drift angles are still too big. We need a discussion for this kind of structure put into use. And last, the energy dissipation. This is the relation curves of the energy dissipation and the circumambulance. We can see as the lateral displacement turn to larger and the more energy consumption the knee brace structure and the fitting lateral wood structure provides. And this is the energy consumption relation curves between the cumulated total displacement, and we can see the fitting lateral wood shear wall structures always providing the best energy consumption. And at last is the conclusion of our experimental studies. And thank you for your attention. And thank you.
Any questions from the studio? In your cross brace,
Yeah.
you put a large bolt in between the two braces.
Yeah.
Why do you need such a big bolt?
Before the experiment, we didn't know the hole will destroy the tension member of the structure. We referred to the design of steel structures, and
So the lesson learned is not to trust the steel guy. No. You cannot use the steel design for wood, right? So
yeah. So from the test, we get some useful information about wood design.
Any other questions? Okay. Thank you very much.
Thank you.
This first morning session is Miss Liu Hui. She's from Tongji University, and she is going to report on tests on lateral resistance of glulam beam to column connections, probably again moment connections.
And I can press this down.
Yes.
Thank you. Good morning, ladies and gentlemen. It's my great pleasure to attend this symposium. My name is Huifeng Liu, a PhD candidate from Tongji University, and my supervisor is Professor He. Today my topic is test on lateral resistance of glulam beam to column connections and the comparison of ductility analysis methods. It mainly contains 4 parts as follows. First, let's move to the introduction. As we all know, bolted timbal connections is one of the most widely used connections in timbal structure. This type of connection is easily installed and could transmit shear force directly. So it's usually used in the post and beam systems as the post beam connections and the column to foundation connections. However, the ductility and lateral resistance of bolted connection is very poor. So in practical design, the moment resistance is usually ignored. However, when they are subjected to loads such as wind and earthquake, this connection may experience loading moment not intended in the design. So it's necessary to employ the lateral resistance of glulam beam to column bolted connections. When it comes to the lateral resistance, another concept must be mentioned, that is the ductility. Because of the high nonlinearity of the bolted connection behavior, it's difficult to define the yield point, and which has a closely relationship with the ductility. So in order to solve these 2 problems, tests on wood, steel wood bolted connections were conducted. Here is the information about the test. There are 4 groups in total, and 2 groups are unreferenced connections, and the other 2 the referenced connections with self-tapping screw. And there are 3 specimens in each group, and on the right is the material information. This picture shows the details of the unreferenced connections NM2 and NM3. In order to make sure the failure occur at the connection region on the beam, there are 16 bolted in the connection on the column, and there are 2 rows of bolts in NM2 and 3 rows of bolts in NM3 respectively. The bolt space parallel to grain is 5 times of the bolt diameter, and the bolt space perpendicular to grain is 4 times of bolt diameter, according to the glulam structure design code in China. And here is the detail of the referenced connections. They are similar to the unreferenced ones. The only difference is that they are reinforced by self-tapping screw with a diameter of 8 millimeters. And this picture shows the screw used in the specimens. They are 130 millimeters in length with partial thread. Because of the limitation of the length, they are not go through the whole beam, so they are punched into the timber from the both sides. And here is the general view of the test setup. All the tests were conducted
in thermal engineering laboratory in Tongji University. And the specimens were loaded by an electro-hydraulic servo-loading system, and the deformation was recorded by the LVDTs. Here, this picture shows the location of the measuring points. The point 1, 2, 3 record the rotation of the beam, and the point 4 and 5 record the rotation of the steel plate. And the test procedure outlined in ASTM was followed. Each specimen is subjected to a displacement control at a rate of 5 millimeters per minute. And here is the failure mode of the unreferenced specimens. From this, we could see that the major failure mode observed is brittle, such as the splitting, roll-out, and tension. And this is the deformation of the bolt and the timber. Both the one plastic hinge and the wood crushing is observed. When it comes to the reference specimens, we could see that there are seldom brittle failure mode. No roll shear out was observed, and only when the deformation is large, splitting occur. And the deformation of the bolt and the timber is similar to the unreferenced ones. And the bending of the self-tapping screw is slight. Here is the load deformation curve. One thing must be noticed is that the capacity of SM3 exceeded the range of the loading system, and it didn't reach the ultimate moment and rotation. So the comparison of NM2 and NM3 is found that the ultimate rotation of reference connection was much larger than that of the unreferenced one. Here is the capacity and stiffness, and in table 1, the failure mode is defined as the 18% of maximum moment, and the elastic stiffness is equal to the slope of the 10% and 14% secant line. Here is the comparison between the connections. And through the comparison between NM2 and NM3, it was found that the bending capacity and elastic stiffness increased by 27% and 7.3% respectively, while that factor of the SM2 and SM3 is larger than 40% and 18%. So it's obviously that increasing the number of bolts could improve the bending capacity and elastic stiffness, especially when the connection was referenced. And through the comparison between the unreferenced connections and the reference connections, we could find that self-tapping screw did contribution to the bending capacity, but their contribution to the elastic stiffness is not so clear. It needs some more further research. And when it comes to the yield point, it seems a little complex because there are so many different methods without one universal approach. Here I give a brief introduction of the most commonly used analysis method. First is the EEP curve, and it's based on the energy equivalent principle and assumed the load deformation curve as a bilinear curve. And here is the offset method. In this method, the yield point is defined as the intersection of the curve with a straight line, which is parallel to the initial stiffness. And when the deformation is displacement, the offset distance is 0.1 millimeters. And when the deformation is rotation, the offset distance is 2 radians per thousand. And here's the bilinear approaches, including the seeing method and the Viking method. They both use the secant line and a tangent line to determine the yield point, and both in both of these methods define the first line as the initial stiffness. The difference is that in C method, the second line is drawn at a slope equal to 1/6 of the slope of the first line, and the intersection of these two lines is defined as the yield point. And in the YK method, the second line is tangent to the curve and parallel to the 14% and 19% secant. And the intersection of those two lines projected horizontal toward this curve to determine the yield point. And here is the proportional limit approaches, including KC method and CSRO method as shown in this picture. And here is the location of yield point determined by the CS method mentioned above. From this, we could see that the yield load determined by EP method was the highest, and the yield point was located off the load displacement curve. And although the CM method and the YK method based on the same principle, but there is a big difference between them. And the yield point determined by offset method, YC method, and CSRO method was basically coincide. And the results of NM3 is similar to NM2. When it comes to the reference connection, it's similar to the unreferenced ones, except that the results of the two bilinear approaches were basically constant, as shown in this picture. It seems that the result of these two bilinear approaches has a close relationship with the deformation of the curve. And the result of SM3 is similar to SM2. And here is the classification of ductility proposed by Smith in 2006. They used the rotation of the displacement according. He classified the ductility of connection into 4 classes based on the ductility region. And one thing must notice is in this classification, the ductility region is defined as the first one, and it's not the region of the failure displacement to the yield displacement. And here is the ductility region calculated by the CS methods mentioned above. From the analysis, we could see that the CSRO result of CSRO and KC and offset are similar. So here I chose the CSRO method to analyze the ductility. From this, we could see that both the unreferenced connection NM2 and NM3 are in the low ductility, and the referenced connection SM2 is in the SM2 is in the moderate ductility as shown in this table. And through the comparison of NM2 and NM3, the ductility region increased by 11%, and through the comparison of SM2 and NM2, the ductility region increased by 14%. And here is my conclusion. First, the KC method, CSRO method, and offset method are generally coincide and could produce reasonable estimates of ductility. Secondly, the connection referenced with self-tapping screw has an increased ductility and bending capacity. And when the number of And if we consider the chamber referenced by self-tapping screw as a new kind of material, It performs better than the unreferenced, both in capacity and stiffness. Of course, because of the limitation of the number of the specimens, more generally concluding need some further research. So okay, that's all. Thank you.
Any questions?
It's a very good presentation. Can you go back to one of the pushover curve for the moment curvature?
This one?
I have a question about from 0 to 2, why the initial stiffness is smaller than the stiffness in the middle.
You mean the initial stiffness?
Yes. Why at the beginning the stiffness is
You mean the beginning at the curve?
from 0 to 2?
Oh, this is because the bolt hole in the timber was drilled with a diameter of 60 millimeters, and the diameter of the bolt is only 40 millimeters. So there is a tolerance between them, and this fabrication tolerance makes the first initial slip.
I'm sure you're aware of the work done at UBC in this area. And our findings are very different from yours in that the increases are quite significant when you apply the self-tapping screws. Why? Can you explain? Have you thought of why there's a difference?
The difference between my work with... I have read a paper published in about 2006 in UBC, kind of the similar test, and I found that the bolted hole they drilled is closely to the diameter of the bolt, and that is the fabrication tolerance is very, very small. But in China, in practical fabrication, it's very hard to reach. And I think the second difference is that in the test conducted in UBC, the self-tapping screw is long along the beam, and here in this in our test, the self-screw is pumped into the timber from both sides. It's not the.
I think also the screws that we use are fully threaded, so every part of the wood is enforced, whereas yours is only partially threaded. So you only enforce the threaded part.
Yes.
Right? So the outer part are not enforced. Right? So you still look at the failure mode, you can see still splitting failure. Right?
Yeah, it's still the. Okay. No. And from the unreferenced specimens, we could see that most of the splitting occur at the outer row of the connection. And so we referenced the bolted just at the outer rows. And from this, we see that slipping also occurred, but the row shaft was not observed.
Any other questions? If not, I'll close the session.